everyone, and welcome to another video. Today I'd like to continue our discussion on linear ordinary differential equations, and in fact this is a direct follow-up to our previous lecture where we actually talked about homogeneous linear ordinary differential equations, right? So if you haven't seen this previous video, right, where we discussed the homogeneous flavor of ordinary differential equations, please take a minute, pause the video, go back and watch this video first, because we're going to build off a ton of the concepts that we presented here. And we're going to see today, all we want to do is, instead of looking at homogeneous linear ordinary differential equations, and remember, just to refresh your memory, last time we looked at a second order linear ordinary differential equation of the homogeneous type, namely meaning there was no input or no forcing function to the system, namely the right hand side of this was 0. That's what we looked at in the last video. What I want to look at today is it's kind of almost like you might think it's a small epsilon change, but we're going to see that it's got some interesting ramifications. But now I want to tack on a prefix to this. Instead of looking at homogeneous linear ordinary differential equations, I want to put on a non prefix. So we're going to look at non-homogeneous linear ordinary differential equations, and all that means now is, instead of the right hand side being 0, let's go ahead and consider that now there's some kind of external input to this system, something like a g of t. Okay? So now, what makes this interesting is this description is almost like a input-output system, where now you've got some system where it is governed by this linear ordinary differential equation, right, that we have here. And again, keep in mind, what we're going to be talking about today is we're going to use this second order linear ordinary differential equation as an example, but this could be third order, fourth order, fifth order, whatever, it doesn't really matter. This whole idea extends to completely higher dimensions and higher orders. But again, what we're saying is that there's some system who behaves according to this differential equation, right? So this thing has some solution x of t. This says, how does the system behave? Again, what is the position of the block or the pendulum or the whatever system you happen to be modeling with this ODE. And now when we have a non-zero g of t, we're basically saying that now there is some kind of an input, like a force or a thrust or a gas pedal position or a torque or whatever you want. There's some input to the system, it goes through some type of dynamics, and then it has some kind of output coming out the far side. So this is an incredibly powerful modeling construct, because we finally have this concept of an input and then finally some kind of output. And all of this interesting dynamics of how the inputs affect the output are now governed through this ordinary differential equation. So this tiny little addition of the non portion actually adds an incredible amount of depth and richness to the problem. So we're able to describe real world systems where you have an input that has some causality and it causes an output, right? So I apologize for getting sidetracked a little bit, but I think this is just so darn exciting, because now this is really going to start opening up a lot of doors and opportunities for us in terms of engineering analysis and modeling here. So now that we've got kind of the big picture with this, let's start talking about how can we, again, if you remember in our previous video, we talked about how could you solve this differential equation if the right-hand side was equal to 0. So all I want to do today is, okay, now that it's not equal to 0, we have some input g of t. This function could be a sine wave, an exponential, a ramp, a polynomial, who knows what it is. How do we see, how does the system respond to that? How are we going to solve this differential equation using these quote-unquote traditional techniques that we saw earlier, okay? So, a couple of things to note. First thing, I want to introduce a little bit of a notation. I don't want to have to keep writing this differential equation of a times the second derivative of the function plus b times the first derivative of the function plus, oops, sorry, there should have been a c there. Whoops, sorry everyone, there should be a c right there. Plus c times the function, right? I don't want to have to keep rewriting that over and over and over and over. So I'm going to define an operator. Let's call this operator q. Okay, this operator q, when you pass it the function x of t, or any function, right, all this thing does, the way this thing is defined is, okay, it takes this function, it takes the second derivative of it, tacks on an a in the front, takes the first derivative of it, tacks on a b in the front, and then takes the function itself, tacks on a c, okay? That's all that function does, okay? So all this allows me to do is I can rewrite that differential equation, and again, keep in mind, this q, if you had a third order differential equation, or a fourth order, or a fifth order, I just don't want to have to keep writing out all these a, b, c coefficients and all these like dots. I'm lazy, right? Mathematicians are lazy, so we introduce all these kind of like additional symbols or notation to make our lives a little bit easier. But that's all I'm saying here is I just want to make my life easier, and instead of having to write all that gobbledygook up there, we would like to be able to write this as basically, okay, q times x of t, right, is equal to g of t, right? That's the exact same notation, okay? And it's just going to make our lives a little bit easier in the future, okay? So now that we've got this, what I want to look at is actually, let's look at a theorem of how solutions to this non-homogeneous system relate to solutions of the homogeneous system. So I'm going to do a little magic, wave my wand, and then I'm going to make this theorem appear on the other side of the board. So there we go. Aha! Okay, so here's the theorem, okay? Let's take a look at this. So let's say you have solutions, let's call them x1 and x2, okay? These x1 and x2, let's say that I don't know where you got them. You pulled them out of thin air. Somebody gave them to you. You cheated and read the back of the book. Who cares? You found these x1 and x2, and they solve the non-homogeneous equation. Meaning, if you plug x1 and x2 into here, you will basically get g of t. It will solve this. It will make the left-hand side equal to the right-hand side, okay? If you're able to find them, well, if you just take their difference, either x1 minus x2 or vice versa, x2 minus x1, doesn't matter. You look at their difference. This quantity here, the difference of x1 minus x2, that's actually a solution to the corresponding homogeneous equation, right? So that means if you put x1 minus x2 into the q operator, you would get 0. Not g of t, you would get 0, right? It's the difference solves the homogeneous equation, not the non-homogeneous equation, right? Okay, so that's what's happening, okay? That's the first thing we're going to want to prove. If we can show that that's true, what we're also going to show that is, in addition, if you had x1h and x2h, right? Those are solutions to the homogeneous equation, right? Which, again, we talked about in our last lecture. If that's true, then this is crazy. Well, no, it's not. Maybe this isn't so crazy here, but basically the difference of solutions to the non-homogeneous are equal to actually a linear combination of solutions to the homogeneous portion, okay? So this is an interesting theorem. Let's go ahead and prove this now to convince ourselves that we're not doing something crazy here, okay? So, tell you what, let's leave some of this up. I can erase this initial condition, right? We all know what this is of the problem, right? This is our initial or our boundary condition. I think I can erase our little picture right here. And everyone remembers our Q operator. Maybe what we're gonna do here is, let me move this up just so we can refresh our memory. This whole side here is lazy speak, or the easier way to do this is q of x of t, right? Okay. Okay, so with that out of the way, okay, let's go ahead and prove that, okay? So, all right, let's talk about the proof. Okay, we'll talk our way through this, okay? So let's look at this first one. So the first assumption, we know that x1 and x2 are solutions to the non-homogeneous equation, right? Okay, so if that's true, then, okay, in order for it to be a solution, right, q of x1 of t, right, what has that got to be, right? Well, it's got to be equal to g of t, right? If this thing is equal to, if it is actually a solution, if it solves this non-homogeneous equation, it means that when you plug in this function x1, again, who knows where you got it, or what it looks like, but when you take its second derivative, multiply by a, take its first derivative, multiply by b, take itself, multiply by c, add them all together, it equals g of t, right? So this has to equal g of t, right? Okay? And by exact same similar logic, if q of x2 of t, right, this has to also equal g of t, right? So if you take this minus this, you're basically taking g of t minus g of t, right? So in other words, if I do q of x1 of t minus q of x2 of t, right? This is, right here, we just saw this is g of t. This is g of t. Well, you take their difference and you better get a big fat 0, right? Okay, now let's examine this left-hand side. Maybe let's write this thing out, okay? So again, let's expand this. So instead of using our lazy Q operator, right, this here is shorthand for AX1 double dot of t, right, plus BX1 dot of t plus CX1 of t, right? That's that side, minus AX2 dot of t plus bx dot 2 of t plus cx2 of t, right? Has got to equal, well, I guess, sorry, this is the left-hand side. I'm just examining the left-hand side of this expression over here, okay? Okay, great, and now this is where it's awesome that we are dealing with a linear ODE. Because you can see what's going to end up happening. We can distribute this minus sign through, right? So I could do this. This would be minus, 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 right? Okay. And with a little bit more algebraic manipulation, let's grab collect the A's. You know, so so basically I could write this thing as AX1 double dot of t, right? Minus x2 double dot of t, right, this thing, plus b x1 dot of t, right, minus x2 dot of t, plus c x1 of t minus x2 of t, right? This is equal to the left-hand side still, right? Okay, so if you look at this a little bit more, right, you can see that, you know what, gosh, I can even pull this, the derivative operator outside. So namely what I could do is, shoot, I ran out of room a little bit. Let's come up here. Okay, so this thing can be a times ddt squared of x1 of t minus x2 of t, right? Plus b times ddt of x1 of t minus x2 of t, right? Plus c times x1 of t minus x2 of t, right? You know what? This difference here, you could call this some other different function. I don't know. Call it like, gosh, I'm going to make something up. Call it a y of t, right? Here's y of t, here's y of t, here's y of t. Right? So if you look at this thing long enough and you stare at it, you see that, hey, all this is doing, right, you take some function y, you take its second derivative, multiply by a. You take the function, take its first derivative, multiply by b. You take the function, multiply by c. You add them all together. That's exactly what this Q operator did, right? This is exactly the definition of our differential equation earlier, right? So we can get this, and we can write this whole thing as basically q, right, of x1 of t minus x2 of t, right? Yeah, right? This is equal to the left-hand side, right? That's equal to this left-hand side. So this is actually interesting. So we're basically saying that, okay, the left-hand side, right, this left-hand side, that's this thing right here, right? This is the left-hand side of the equation. So let's just jam that in here. So this is q of x1 of t minus q of x2 of t, right? Right? Okay, great. And now we're going to use this fact. What is q of x1 of t minus q of x2 of t? It's equal to 0, right? So this over here is a big fat 0. So we have q of x1 of t minus x2 of t is equal to 0. Right? What does this actually mean if you think about this? q of a function, right, is this portion of the differential equation. So we are basically saying that this function, whatever it is, we called it y here, right? It's basically the difference of x1 and x2. Its difference, by the time you plug it in and run it through this linear ordinary differential equation, you would get not g of t, you get 0, meaning that this here has to solve the homogeneous portion of the corresponding ordinary differential equation, right? So this difference here, x1 of t minus x2 of t, solves the homogeneous ODE. And sorry, I did not manage my space very well, but this is what I'm circling in red here, right? This is what we were gunning for, right? That is exactly what this portion of the theorem states, right? So we just proved the first portion of this. If you have x1 and x2 of t, again, I don't know how you got this. You begged, borrowed, or stole the solution, right? You got it somehow. x1 and x2, they solve the non-homogeneous differential equation, right? All you do is, once you have two solutions that solve the non-homogeneous differential equation, this guy here, you take their difference, and the difference will actually solve the homogeneous ODE, right? Wow, that's pretty darn interesting, right? Okay, so we proved the first portion of that theorem. Tell you what, give me a second to pause the camera, erase this side of the board, and then we'll deal with the second part of the theorem. Okay, so we got a little bit more whiteboard space, and again, just to reiterate, we just proved the first portion of this theorem, right? All these words in English boil down to showing this was true, right? Q of x1 minus x2 is equal to 0, right? That's what we just showed. Now, let's work here on this second part, right? Okay, so what does that second part say? So it says if we've got x1h and x2h, and those are solutions to the homogeneous equation, let's stop there. What does this first bit in green allow us to say? So this first bit in green here, okay? What does that mean? Well, again, if you think about it long enough, what that means is that, okay, if you take x1h of t, this thing, you take its second derivative, multiply a, you take its first derivative, multiply by b, you take itself, multiply by c, you add them all together, you get not g, you get 0, right? In other words, if you take the q operator of that, right, my lazy hand speak, instead of just plugging that in, here's my lazy way to do it, you better get a big fat 0, right? That's what it means, okay? And then, similarly, q of x2h of t is also 0, right? Now here's what's interesting. If you remember, again, in our previous video where we talked about homogeneous linear ordinary differential equations, we showed that if you have these two solutions, linear combinations of those solutions are also solutions to the homogeneous equation, right? So we showed in the last video that basically you take a c1 x1h of t, right, plus c2x2h of t, right? All this is, this thing right here, this quantity, it's a linear combination of solutions to the homogeneous ordinary differential equations. Well, this guy is also a solution to the homogeneous linear ordinary differential equation, meaning, again, if you go ahead and take this q operator on this thing, you also get a big fat 0, right? Awesome. So now, what's interesting is this is equal to 0. And you know what we just proved here in blue? We said that the difference of solutions to the non-homogeneous were also 0, right? After you pass it through the operator. So what I'm saying is, okay, another way to write 0 is I could also say q of x1 of t minus x2 of t, right? And heck, let's get rid of this 0 in the middle, right? It's just basically this is equal to this, and everything equals a big fat 0, right? So maybe the easier way to look at this is let's set these two equal to each other, right? They're all equal to 0 at the end of the day, right? So if you look at this and you think about this long enough, the way that they're 0 then is the arguments to the q operators, they have to be the same, right? In order to do that. In other words, I can get rid of that q operator and I can just write c1x1h of t plus c2x2h of t. is equal to x1 of t minus x2 of t. Right? And bam, that's what we're looking for. Right? Because that is what we are looking for, or what the theorem kind of claimed, right? So there's the proof, okay? So what's interesting about this is we can now leverage this to come up with a total solution to the original non-homogeneous linear ordinary differential equation, okay? So to do that, all we need to do is rewrite this a little bit. So again, give me a second to erase. I think we're done with this theorem, right? Because this is kind of where we wanted to end up with. If you believe this, we can basically go places. So yeah, give me a second. I'll erase the theorem part. We'll move this key result higher up, and then we're going to build off of it. All right, so this is what we just showed, right? That x1 minus x2 is equal to c1 x1h plus c2 x2h here. And again, remember, x1 and x2 here, these guys are solutions to the non-homogeneous ODE, right? So really, this is what we're looking for. We're looking for either x1 or x2. That's kind of what we're trying to solve for, right? x1h and x2h are solutions to the homogeneous ODE, and again, we know how to solve for those via, because I mean, we talked about that in our immediately preceding lecture about how to solve a homogeneous linear ordinary differential equation. So that's what x1h and x2h are. Those are solutions you get out of that. And again, c1 and c2, these are just constants that, again, we're going to see are helping us satisfy initial conditions or boundary conditions of the problem, right? So all we need to do here is really, again, we said we're looking for x1 t or x2 of t, one of those two. Let's just say I want x1 of t, okay? And then this is a little bit of slightly circular logic. You're gonna have to just bear with me. Why don't I just move this to the other side? Let me move x2 to the other side. So let me write this thing here as x1 of t is equal to c1 x1h of t plus c2 x2h of t plus x2 of t. Right? And again, what we're looking for is we're looking for this. This is like the total solution to the non-homogeneous linear ordinary differential equation. So this is what we're looking for. We want this thing. This is like the complete, or sometimes referred to as the total solution of the problem. So I don't know, let's give this maybe a different symbol. Instead of x1 of t, let's call it phi of t. Sometimes you might see some textbooks call this like the total solution or whatnot. Okay, then this is equal to c1 x1 homogeneous of t plus c2 x2 homogeneous of t, of t plus, and again, what is x2? Okay, again, it's a solution of the non-homogeneous differential equation. So again, this is where it's a little bit backwards, right? This was the solution we're looking for, but now I need to add on some particular solution. Like, it doesn't have to be the complete solution, it just has to be a solution, right? It's kind of, I'm just looking for one. So I don't know, you can call this like xp for x particular. You'll sometimes see that in textbooks. Right? So this is our total solution. So the total solution you see here is a combination of the solution due to the homogeneous system plus some portion which is somehow related to this input g of t, which I guess, oh, whoops, I guess we erased some here. Okay, so again, I think this is going to help when we go through an example, but I just wanted to write it out and show it because we actually do gain a little bit of insight to this. Let me just go ahead and maybe I'll rewrite this again. So this portion here, we see that the complete system response. So again, remember, this is like the position of the block or the pendulum or the velocity of the vehicle or whatever you're trying to model here with your differential equation. This is what it does, right? This is a complete solution. Its trajectory or its solution here is a portion here due to blue, and this here you can see is almost like, it's sometimes referred to as the autonomous response. You know, again, also the homogeneous response. right? Because again, it has the solution, which is x1h and x2h. It's a linear combination of that, right? And remember, x1h and x2h, those had nothing to do with what was going into the system, right? Again, our system looked something like you put in a g of t and out comes x of t, right? The trajectory of the system. This x1h and x2h had nothing to do. It didn't matter what you did. It was almost like the system's natural autonomous response, right? Without any input. What it would do by itself, right? That's this portion here in blue. But then, because we are inputting something like some kind of forcing function, like a sine wave or a polynomial or, you know, a chirp signal or whatever you're putting in, there's also this portion here. So this is like the non-homogeneous response. Sometimes you might hear this called like the forced response. Right? So it's really, really darn interesting. From a mathematical standpoint, we see that the entire trajectory, right, what the system is going to do, it's going to be a combination of what it wanted to do by itself, irregardless or irrespective of what type of inputs we're using, plus obviously it's going to respond in some fashion to the inputs to this system here, right? So pretty darn fascinating, right? What this equation also allows us to do is it allows us to start thinking of a kind of like an algorithm or a recipe or a cookbook of how could we go about solving for phi of t, right? Which was our total solution of what we're looking for, right? So again, what we're going to want to do here is let's just quickly write this out. So again, maybe let's just go ahead and restate the ODE, right? The non-homogeneous. Right? We said this is something like ax double dot of t plus bx dot of t plus cx of t is equal to g of t. Right? That's what we're dealing with, okay? And again, we're solving for x, which I guess we call phi, or the total solution, or however you want to think about this, right? So, according to this cookbook here, you see, we need to do two things. First, we need to find the homogeneous response of the system. We need to find the solutions to the homogeneous differential equation. So, step one here, right, is we basically need to find the general solution to the homogeneous system, right? And what that basically gives us is it gives us C1x1 homogeneous of t plus C2x2 homogeneous of t, right? That's what we'll get if we're able to complete step one. And again, you complete step one by basically watching the previous video to this, where we talked exactly about how to get this. What do you get x1? How do you get x2? How do you get C1 and C2? Although that's a slight little... Maybe I better pump the brakes right now with this C1 and C2. We'll see that you need to actually, you can't solve for the C1 and C2 right here in step one. We're gonna have to delay that process. But you can definitely find what is x1 homogeneous and x2 homogeneous, right? You can find solutions to the homogeneous system at the end of step one, okay? Then what you're gonna do here is in step two, okay? What else is on the right-hand side of this equation? We nailed this. We need this guy, right? So step two is we need to find a particular solution. Again, maybe we should put in parentheses, you know, AKA a single solution, right? You just got to find one solution which solves the non-homogeneous differential equation, right? So we need to find a particular, or one of them, or a single solution to the non-homogeneous system, right? Or ODE, right? That is going to give us that xp of t, right? And then, according to our little equation over there, step three is just add the results from step one and step two together to obtain the total solution of the non-homogeneous system, right? That's what we were gunning for, is the solution to this thing. Again, this is what we're trying to solve. I want the total solution. So again, it's a little bit circular in the sense that, okay, first you find the homogeneous system, and then here's the circular part. To find the total solution to this non-homogeneous differential equation, you got to find one solution to start with, and then you add it together to get the total solution. So that's the game plan. So I think what would drive this home is, let's look at this for two concrete examples and go through all the steps, and I think it'll make a lot more sense after that. All right, so the technique we'd like to use or examine now to solve these non-homogeneous ODEs is using what's called the method of undetermined coefficients. And in particular, this is how we're going to find that particular solution that we need, okay? So let's look at an example here of a non-homogeneous ODE with an exponential forcing function. So again, here's the ODE portion, and here's g of t, or the forcing function input. And as you can see, it's an exponent of the form 3e to the 2t. So again, here are the initial conditions for this differential equation. So the picture that goes along with this, right, is you basically have your system, which is governed by x double dot plus 3x dot plus 2x, right, with these initial conditions here. And now what's going into this is you're going to use an input of a function of 3e to the 2t, and we now want to know, what does x of t look like, right? And we now know that this is the homogeneous response plus the particular response, right? So the goal is to find the homogeneous and the particular response and put them together to get the total response of the system, right? That was our game plan. Okay, so let's go ahead and get started. So the first thing we want to do, if you remember, was step one, right, was basically find the homogeneous response, right? And we saw how to do that already, right? We said, okay, just consider the characteristic equation of the homogeneous portion only, of just the ODE, right? So we need to find the root. So this is, the characteristic equation of this is r squared plus 3r plus 2 equals 0, right? So go ahead and solve this just like we did in our previous lecture, and I think you're going to find out that the roots of this, you got a root here at r1 at -2 and a root 2 at -1, right? So from that, we can basically formulate the homogeneous response, right? xh of t, right? This is just c1, what do we say? c1e to the r1t plus c2e to the r2t. Again, if you're not familiar with where this came from, watch the previous lecture where we looked at how to solve homogeneous linear ordinary differential equations. Okay, so again, we can plug in our r values. So we have c1e to the -2t plus c2e to the -t, right? So here's the homogeneous response right off the bat, okay? Now, the thing that we maybe want to make a note of here, do not apply your initial conditions yet, right? You remember last time in the homogeneous situation, we could find C1 and C2 by basically applying the initial conditions up there, but we're gonna wait, we're gonna do that later, okay? So don't do this, just leave it in this form of C1 plus e to the -2t plus C2e to the -t, okay? All right, great. So the next thing that we needed to do, step 2, was basically find, right, a particular solution. And this is where it goes a little bit clang in my head, and hopefully goes a little clang in your head too, because what we have to do is we have to basically, I guess, literally guess at this, or pull a function out of thin air that we know is going to solve this non-homogeneous ODE, okay? So we know that what you're going to end up using is going to be keyed off what form does g of t take. So in this case, since g of t is an exponential function, I happen to know that a family of functions that is going to work is going to look something like a constant or a coefficient a times e to the 2t. And again, this should be going a little bit clang in your head because you should be like, where did you get that? It looks like you're pulling a rabbit out of a hat, right? It's like you just knew this off the top of your head. And again, keep this in mind because in a second, we're gonna compare this with the Laplace technique, which is actually vastly superior because it gets around this problem of needing to know this information a priori, right? So if you let's continue with this, and if you assume that this works, let's just walk through a couple other steps and see how this shakes out, okay? So we're gonna propose this, right? So this is a proposed solution, okay? And it has an coefficient which is underdetermined right now. Oh great, I spelled underdetermined. Right? like in our title here, right? It has this underdetermined coefficient. Right? So the goal now is we got to find an A that is going to quote unquote work. And when we say quote unquote work, well, we mean that this solution, it has to solve the differential equation, right? So if I were to plug this particular solution through the Q operator, right? In other words, this ODE, this had better equal G of T. Right? That's what it means to have a particular solution which solves the non-homogeneous differential equation, right? Is you evaluate it, it gets G of T. Okay, great. Let's just write out the left-hand side. So the left-hand side, this is just ddt squared, right? The second time derivative of xp. Well, xp is, this is what we're proposing, right? It's a e to the 2t, right? Plus 3 times, what is it? ddt of a e to the 2t. Right? Plus 2 times a e to the 2t, right? And that has to equal G of T. Well, what is G of T? It's right there, right? It's 3e to the 2t, 3e to the 2t, right? Okay, great. Let's just expand, do one more line here on the left-hand side. Okay, you take the derivative of this thing twice. What do we get? This is now becomes 4a e to the 2t, right? Okay, plus 2, so this is plus 6a e to the 2t, right? Plus 2a e to the 2t. That's got to still equal the same thing, right? 3e to the 2t. Okay, great. Collect all of these terms. I think we end up with, what is this? This is 4, 10, 12. Okay, so this is 12a e to the 2t has got to equal 3e to the 2t, okay? So you look at this, you solve this thing. This cancels with this. Move that to the other side. So a had better equal 3 over 12, or what is this, 1/4? Great, okay, so we found a the coefficient. So we determined the underdetermined coefficient. So this basically gives us the degree of freedom that's needed to make this function work out, right? So we see that really the particular solution, it's not a e to the 2t, it is 1/4 e to the 2t. This is a particular solution of the problem, right? Okay, so great, we've got that. Now let's go on to step 3. Tell you what, give me a second to pause the camera, erase the board, and we'll move on to step 3, where we basically add this together with this to get the total solution. All right, so now we're on to step 3, and step 3 was basically just go ahead and form the total solution, right? The total solution we saw was the homogeneous portion, which was what? It was c1 e to the minus 2t plus c2 e to the minus t, so that was the homogeneous portion, plus the particular portion which we just solved for, which we said was 1/4 e to the 2t, right? Okay. So great. So now what we need to do is we can now finally go ahead and apply the initial conditions, right, in order to find C1 and C2. So now let's go ahead and apply ICs to find C1 and C2, right? Okay, so what was the first initial condition? I need x at time 0, right? So I need the solution at time 0. Well, I can get that by, that's just C1, and then everywhere I see a t, stick in a 0, right? So this is e to the negative 2 times 0 plus C2 e to the negative 0 plus 1/4 e to the 2 times 0. Right? Okay, so what is this thing? This is now C1 plus C2 plus 1/4, right? And that is equal to x0. Well, what is x0? That is 3, right? Okay, great. So box this guy up. Here's one equation for two unknowns, okay? So now let's go ahead and apply the second initial condition where I need x dot at 0, okay? So first let's compute what is x dot at 0. So I got to take the derivative of this whole thing, right? So I need to take ddt of c1 e to the negative 2t plus c2 e to the negative t plus 1/4 e to the 2t. Take the derivative of all this, evaluate it when time is equal to 0, right? That's what the initial velocity of this should be. Okay, so let's go ahead and work this sucker out. What is this? Negative 2c1 e to the 2t plus, no, negative, right? Minus c2 e to the negative t plus 1/2 e to the 2t, and then all of this needs to be evaluated at t equals 0. So this thing is, I guess this, what do we get? Negative 2c1, right? Because that goes, this e goes to 1, minus c2 plus 1/2, right? Okay, that should be the initial velocity, x0, or x dot at time 0, and we saw that has to equal negative 2, right? Great. So here we go. So now we got two equations for two unknowns. Let me just make sure I wrote that down correctly. Minus c1 plus a half. Yeah, okay, great. Okay, so solve these two things simultaneously, and you'll basically get simultaneously, and we're going to basically get c1 has got to equal negative 1/4 and c2 has got to equal 3. So we're basically done. So here's our total solution. So the overall total solution, right, which we called earlier was phi of t, or the total solution, or x of t, whatever you want to call it, right? This is negative 1/4 e to the negative 2t plus 3 e to the negative t plus 1/4 e to the 2t. Right? Great. So box that up. And again, this is where it becomes very interesting and clear that, again, we have this portion here, which was the autonomous or the homogeneous response, right? This e to the negative 2t and e to the negative t, those are remember the roots were at r1 of negative 2 and r2 of negative 1. That's where you get these two terms here, right? So these two exponentials come from the system itself. It has nothing to do with the input g of t, nothing to do with the input force here, right? But now we have the second term right here. This is the particular, and this is the forced response, right, so to speak. So this guy, obviously you can see, looks very similar to this, right? But also note, this is not equal to g of t, right? This is g of t over here, right? So this function is interesting in the sense that this term and this term, if you look at this, as t gets large, these are going to go away to 0. So the response of the system due to initial conditions, that's what these two are, they're effectively going to die away. These are your initial transients, and what's going to end up is the only thing as the limit, basically, right? If you look at this thing, the limit as time goes to infinity, right, of x of t, it basically looks like the limit as t goes to infinity of just the particular portion, right? Right? This is the only term that remains. And again, what we notice here is that this function, the function that it goes to 1/4 e to the 2t. This is not equal to g of t, right? Which again kind of makes sense if we think about this system as an input-output system here, where you have g of t going in and x of t going out, right? There's nothing to say that the output of this system is going to necessarily track the input of the system as time goes on. So in this particular case, we see that the input, right, this is 3 e to the 2t, and the output here is actually 1/4 e to the 2t. So if we were to plot this thing out, what I would expect this thing to look like is, you know, you got t here, and then you've got x of t, or g of t. I guess we can plot both of them. Let's plot both of them just for giggles here. Let's do x of t in black, all right? And maybe let's do g of t in red. Okay, so g of t is 3e to the 2t. So I don't know, it looks something like I don't know, I'm gonna make this up. Right, maybe we should plot this out for real in Mathematica or MATLAB later, right? So here's g of t, right? This is the function 3e to the 2t, right? And now what the actual x of t does is it does this, right? So there's going to be some initial weirdness due to these two initial the response to the initial conditions, right? And then they're going to die away. So I don't know, I'm going to make this up. I'm probably not doing a very good job of this. And again, I don't know, I'm just sketching this, you know. So, you know, maybe something like this, right? So there's transient response here, right? So this is transient response. But eventually this transient response, this autonomous or homogeneous response, or the response due to initial conditions, however you want to think about it, eventually these are going to die away because these roots are negative. Okay, so this will go away to 0 and you're only left with this force response. And eventually this thing, you know, somewhere around here, you know, I don't know, we'll make this up. Eventually this thing goes and starts looking a whole lot like 1/4 e to the 2t, which again is not equal to g of t, okay? So, fascinating. I think we gain a lot of insight into how linear ordinary differential equations behave in a non-homogeneous situation. So again, the way to think about this, or if there's one takeaway that I want you to have from this discussion, is that the solution to this system here, right? This is your dynamic system, which is governed by your differential equation, right? Its response has a portion which is due to the initial conditions and basically due to the inherent behavior of the system, or how it's built or how it behaves, right? That's what these two roots capture, right? So it's got a component that's related to that, and it also is going to have a component which is directly related to the type of input forcing function that you're sending into the system, right? Which again makes sense. You've got a plane and it's flying along. This plane has some kind of behavior just due to how it's built, to you know, how big the engines are, where the tail is placed with respect to the center of gravity, you know, how long are the wings, what are the camber, all these kind of stuff are going to get buried into these R1 and R2, right? And then it depends on how do you start the plane, you know, is it pitched up a little bit, is it going fast, is it going slow, is it rolled over? There's some initial conditions, right? All of that inherent behavior is going to be captured in the homogeneous portion of the response, right? But now if you have the pilot putting in inputs to the stick in like a sinusoidal fashion, right? That's what this g of t term is going to capture, right? So they're inputting some kind of forcing function or some oscillations or whatever, and the system, the airplane, is definitely going to respond to those, as you see here in this particular solution portion, right? So okay, that is pretty awesome. So what we want to think about though is, okay, here's the answer we got to. We saw we had to go through all this. The one thing that hopefully that should have probably gone clang in your head is the fact that we had to know what the family or what the particular solution family should look like when we did this method of undetermined coefficients. So what I want to do right now is let's look and compare and contrast this with what if we tried to solve this non-homogeneous differential equation using the Laplace technique instead. Okay, so now let's tackle this same problem but use the Laplace technique. So again, I'm going to assume that you've watched all of these videos where we talked about what is the Laplace technique, how to do the partial fraction expansion, how to do the inverse Laplace transform, all of that kind of good stuff. So since I'm going to assume that you've watched that, I'm going to go a little bit quickly through this so we're not rehashing the same material, okay? So to do this with the Laplace transform, I'm going to Laplace transform the left side and Laplace transform the right side, right? So again, this could be written as Laplace transform of x double dot of t, right, plus 3 times the Laplace transform of x dot of t plus 2 times the Laplace transform of x of t equals 3 times the Laplace transform of e to the 2t. Okay, now left side, this all makes perfectly good sense, and I think we can be able to do this no problem. That should be s squared x of s, right, minus s times the initial condition in position minus the initial condition in velocity, right? So that's this first term, plus 3 times sx of s, right, minus the initial condition in position only, because this is a single derivative, right, plus 2 times x of s. right, okay, is equal to 3 times, now here's where the power comes from, right? Here, I don't need to guess at what a particular solution is. I just go ahead and perform the Laplace transform or run the Laplace integral on this exponential function, which we saw earlier. It's just running an integral, right? And you can calculate that and directly calculate it without needing to guess at any types of underdetermined coefficients or anything like this. So this forcing function directly translates via the Laplace transform into this thing, right? 3 over s minus 2, right? That's what you end up with, okay? So now all we gotta do is go ahead and plug in the initial conditions. So this here is 3, this is -2, and this here is 3. And again, you see, we end up in an algebraic expression for x of s. So I go ahead and solve that, guys. So I'm just gonna say dot, dot, dot. I'm gonna assume that you can solve that algebra and get yourself to the point where this x of s, if you solve this thing, it's gonna look something like 3s squared plus s minus 11 all over s minus 2, and then s squared plus 3s plus 2. For the denominator, okay? Okay, so now what we're going to do is, again, like we need to do for our partial fraction expansion technique, is go ahead and solve for the roots of this denominator. So we're going to see that we have roots here at s is equal to, well, you can pretty much read it off here. S equals plus 2, and then this guy, we already know what the roots of this. This is the characteristic equation we saw earlier. So there's a root here at -1 and then -2, right? Okay, so if that's the case, we know that the proper form of this partial fraction expansion is going to be something like an a1 over s minus 2 plus an a2 all over s plus 1 plus an a3 all over s plus 2, right? Okay, and I'm going to assume again that you know how to do this partial fraction expansion and compare the coefficients and all that kind of jazz to solve for what a1, a2, and a3 have to be to make this left-hand side equal to the right-hand side. And I think what you're going to end up with here is you'll end up with what this thing looks like is a1 is going to look like a quarter all over s minus 2, plus an a2 is going to be 3 all over s plus 1, and then plus a negative a quarter all over s plus 2. Great. All right, so this is what x of s looks like. So here's the signal in the Laplace domain. To get this thing in the time domain, all we need to do is perform the inverse Laplace transform, right? So I'm just going to inverse Laplace transform all of that junk, right? That expression for x of s. And here's where the beauty is because I can directly tell this already looks like, you know, 1/4 over e to the 2t, right? So this first term there, I inverse Laplace transform this. This is going to be 1/4 e to the 2t, right? Plus this thing here is going to be a 3e to the minus t, right? And then this one I can basically see it again directly. This is minus 1/4 e to the minus 2t, right? So here's x of t, right? Which is the exact same result we obtained earlier, right? So I think the Laplace technique is vastly superior because, as you saw, it all came down to this. I didn't need to guess at what were the underdetermined coefficients or what type of family of functions is going to make this happen. I just turn the crank on the Laplace transform technique and it will basically pop out the solution for us, right? So that's pretty interesting. So we could go ahead and now, I guess if you really wanted to double check, what you could do is you could double check that this x, basically you plug it back into the differential equation, make sure that it turns into 3e to the 2t, so it satisfies the ODE. Then you could go ahead and check and make sure that it evaluates to 3 at time 0 and that its slope at time 0 is -2, right? You could all do that in Mathematica. And actually, tell you what, to get a little bit more practice, let's look at one more example. We'll talk about it briefly on the board, but then let's actually do it mostly in Mathematica. Okay, for this next example, let's look at the exact same differential equation with the same initial conditions, but let's just change the forcing function. So instead of using an exponential as the input, let's just change this to, how about like a quadratic or a polynomial effectively. So let's make this thing, how about 4 minus t plus 3t squared. So it's just a different input. So it's this quadratic input now. Okay, so let's go ahead and do this. So again, step one is basically the same as before because we didn't change the homogeneous portion of this, right? So the roots of this thing are still at -2 and -1. So we still have a homogeneous solution of c1 e to the -2t plus c2 e to the -t. That didn't change, okay? So the thing that does change now is step 2, where we need to find x particular, right? And this is where, again, it gets a little bit wonky because we need to pull this thing out of thin air, or using our experience of what types of families of functions are going to work for this particular type of g of t. Well, we know that, okay, it's a polynomial in t, so let's choose another polynomial in t as a particular solution. So we're going to choose something like, how about like an a0 plus an a1t plus an a2t squared. Okay? All right, so now what we need to do is we need to go ahead and see what are these a coefficients need to be such that we can make this a particular solution of the differential equation, meaning it is equal to g of t, okay? So tell you what, this is a little bit tedious. Let's go ahead and do that in Mathematica here. And in fact, maybe we can do the rest of the workflow in Mathematica. Once we find this particular solution, then we'll go ahead and put together our total solution. So let's do this. Then the next step, right, we'll do in Mathematica is total solution, right, which is x homogeneous plus x particular, right? We'll put those two together, and then we'll go ahead and check to make sure that it satisfies the differential equation and the initial conditions. We'll plot it, and then maybe we'll also do it in the Laplace technique, again, just to make sure we're all on the same page. All right, so for ease of reference, I've just rewritten the problem here in Mathematica so we can stare at it. The first thing we should probably do is let's go ahead and define the function g of t. So we see that's 4 minus t plus 3t squared, okay? So let's get that into Mathematica. And now what we can do is let's go ahead and get the homogeneous solution, right? And we already saw that that was, we saw the roots were at -2 and -1, so the homogeneous solution was just c1 e to the r1t plus c2 e to the r2t, and we are going to leave c1 and c2 unsolved right now, and instead what we're going to do at our next step is get the particular solution, right? Okay, so again, we saw in this case, for this family of g of t, or for this family of forcing function, we were going to use something like an a0 plus an a1t plus an a2t squared. Okay, so again, we get that into Mathematica, and now in order for this to be a valid solution, it has to satisfy the differential equation, right? Q of x particular of t has got to equal g of t, okay? So let's work on the left-hand side for now. So let's make a function called left-hand side of t, and that's basically, I need to shove this particular solution into the differential equation. So that's, I need to take the derivative of xp of t with respect to t twice, right? That's the second derivative, plus 3 times the first derivative of the particular solution with respect to t, plus 2 times the particular solution by itself, right? Okay, so if I can shift enter this, and this is what we end up with. Now, what I want to also do is let's expand this and then collect terms in descending powers of t. So in other words, let's first go ahead and wrap this with an expand. Okay, and I'll shift enter that so you can see what I mean. So this is expanded. Now let's group all the coefficients of powers of t squared, group all the coefficients of t, and group all the constants. So in other words, I want to collect all of this junk with respect to t and t squared. So all this is doing is just rewriting the equation. So here you go. So now what we see is we actually can now see what do A0, A1, and A2 have to be in order to make this left-hand side equal g of t. Well, if you look at this, I prepared this off screen, I'll just write it down here. You can see that in order to make this equal, I need the constant term here, which is this term here, right? I need the constant to be equal to the constant here, which is 4, right? So I need this to equal 4. Let's look at the coefficient of t. So here's the coefficient of t, 2a1 plus 6a2, right? That has to equal the constant of t up here, which is -1. And finally, the coefficient of t squared, this thing here, right? 2a2, that better equal the coefficient of t squared up here, which is 3, okay? So I need to solve these 3 equations for the 3 unknowns simultaneously, right? So I need to solve, and again, I guess so instead of just copy pasting it, let's do this programmatically. Let's get the coefficient of t squared first. So let's get left-hand side of t, right? That's this entire expression here. I only want the coefficient of t squared. So let's wrap this thing in a coefficient of t squared, right? So does this make sense? This expression here ought to evaluate to 2a2, right? I need that to equal the constant here of 4, right? So I need that to basically be g at 0, right? That's up here when t is equal to 0, I get 4, right? Oh, wait, no, so I'm sorry, excuse me, I'm doing the wrong thing. I want the coefficient of g of t squared, right? Because I'm matching that coefficient first, right? Okay, so that's my first equation. So I actually need multiple equations, so I need a list of equations. So I'm going to go and put some square curly braces here. So that's my first equation, comma, I'm going to enter in my second equation. So the second equation is I need the coefficient not of t squared, but I need the coefficient of t to equal the coefficient of t, right? And then finally, the last thing I need is I need the constant to equal the constant. Well, I can't quite use the coefficient function here, but I could do this. I could do LHS of 0, right? I think you'll agree that this right here, this is going to evaluate to this constant term here, right? Because it's basically going to evaluate this left-hand side when t equals 0. It's going to knock out these other 2 terms here. We're just going to be left with a constant, right? And again, I need that to equal the constant of g of t. So I need g of 0, something like that. There we go. So I'll end curly brace. Here's my 3 equations. I want to solve it for 3 unknowns. So I'll say comma, and then I'm going to ask it for the coefficients or the variables to solve for. I want A0, A1, A2, right? So there we go. That, and then I think we can basically go, here we go. So we end up, here's our answer. A0 is 8, A1 is -5, A2 is 3/2, right? Okay, so again, I guess if you want to programmatically extract that, what we can do is I can assign this to some temporary variable, and then what I'm going to do is I'm going to say A0 is going to be A0 /temp/1, because that's the first solution in this list. Okay, and I'll do the same thing for the other ones. So again, the /dot is just is the replace operator, and all this is doing is so I don't have to copy paste these answers, but here we go. Here's A0, A1, A2. Okay, so, whoopsie, sorry, I clicked on the wrong thing. So, our particular solution now looks like this. Here we go. All right. So, we've got a particular solution. Now we can go ahead and do step 3, right, which was form total solution, right? So, x of t, right, is just the homogeneous plus the particular, right? So, shift enter that. Here we go. Okay, so now that we've got the total solution, we can go ahead and apply initial conditions to find C1 and C2, right? Okay, so, all right, let's go ahead and see what is the initial condition here. So this is 8 plus C1 plus C2. We need that to equal, what do we say it was? It needs to equal 3, okay? And let's go ahead and get an expression for x dot. So x dot... right, we can easily do that. Like, let's call it xd of t, right? This is just dx of t with respect to t. So that's x dot. So xd at time 0 is this term. And again, we need this to be equal to -3. So again, we just need to solve 2 equations for 2 unknowns. So let's go ahead and say solve x of 0, whoops, has got to equal, did we say 3? Yeah, right? And then x dot at time 0 had better equal -2, right? And then solve this for C1 and C2. And again, let's do our same trick of let's assign this to a temporary variable, and then we will extract the answer of C1 is C1/.temp, the first solution. C2 is going to be C2 replaced with whatever the solution is, like such, okay? So, wha-bam, there we go, 2 and -7. So finally, we've got our total solution right here. So this is the entire solution of the problem. So let's go ahead and verify that this satisfies ICs, right? And in fact, it's got to, because we just solved for it right here. So I can basically make sure that x of 0, this has got to equal 3, and x dot at time 0, this has got to equal -2. So look at that, true. We're all golden. So now let's go ahead and verify that this satisfies the ODE, right? So we need to go ahead and take the derivative of x of t with respect to t twice, and then add this thing to, gosh, what was our original ODE? Gosh, I need to, let's scroll back up here, and maybe I'll copy, paste this down here just so we can stare at it. Okay, all right, so this plus 3 times x dot, right, plus 2 times x of t. Right? This better equal g of t, right? That's the non-homogeneous differential equation we're trying to solve. So let's shift enter that. Okay, I think that's the same. We just need to full simplify this thing. And there we go, true. So it totally worked. Okay, for giggles, let's go ahead and now plot the function. The function, right, aka the total solution, right? So I can go ahead and say plot x of t, let's go from t from 0 to 10 seconds or something like that, right? So here's what this thing looks like. And again, we see that x of t doesn't necessarily equal g of t. In fact, if we want to, let's plot g of t on the same plot so we can stare at both of them. So there you go. So x of t is in blue, g of t is in orange. And again, we see that there's similar behavior, but they're not exactly the same. Okay, and now let's go ahead and compare with the Laplace technique. Whoops, I spelled that wrong. Technique. Okay, so the Laplace technique is actually pretty darn simple, right? So what we need to do is we are going to go ahead and first. Let's go take the original differential equation. Okay. And again, I've sort of prepared some of these off screen so you don't have to watch me typing this all in. And now what we're going to do is we're going to take the Laplace transform of both sides just like we did earlier. And again, I've kind of got this prepared off screen. I'll just paste it in here so you can see what we're doing. But again, it's the exact same thing we did on the board earlier. So I'm just Laplace transforming both sides. And now I need to basically take this algebraic equation and solve it for x of s, right? So again, let me just go ahead and paste this in from off screen. So I'll clear x, but then I'm just going to solve this algebraic expression for big X, right? So let's go ahead and see what we end up with. Then here's the polynomial, right? So this is what we end up with. So at this point, we could do manual partial fraction expansion and inverse Laplace transform. But I'm lazy. Let's just go ahead and use Mathematica's inverse Laplace transform, and we'll give it x of s and say transform this from the s to the time domain. So this is going to do the manual partial fraction expansion that we talked about and the inverse Laplace transform. And this is going to give us the total solution. Let's call it maybe x Laplace. This is the same thing that we got. Or this is the time domain signal, but obtained via the Laplace technique. So let's shift enter this, and if you look at this, this is the exact same thing that we got earlier. So let's just check that, right? X Laplace of t, is this equal to the total solution we got earlier? And yes, it is. So in summary, you can see that the Laplace technique is a lot more straightforward and easy to do, and I actually like it a lot better, although it maybe doesn't give us as much insight into the problem as the traditional approach of solving non-homogeneous linear ordinary differential equations. Okay, so with that, I think that's the end of this example. Let's jump back to the board and quickly summarize what we've discussed today.
All right, so let's summarize. What we talked about today is if you were given a linear non-homogeneous ordinary differential equation, as you can see here, with appropriate initial conditions, we saw that there's basically two ways to go about solving this problem. You can either do the traditional approach, right, which we've kind of outlined here. So the first thing that you're going to do is solve the characteristic equation to obtain the roots of this system, right? In this case, R1 and R2, right? Using the characteristic equation. Once you have that, you can go ahead and form the homogeneous solution, right? And we saw in our previous video that there were different cases for what the homogeneous solution could look like. You could either be in the case of real distinct roots, repeated roots, or complex conjugate roots. In this example, I'm using an assumption that that you have real distinct roots, so you would have this type of a homogeneous solution. If you're in one of these other cases, the format of the homogeneous solution just looks a little bit different, right? But that's all you do. You basically solve for the homogeneous solution. Then step 3, this is again the part where I don't really like the traditional approach quite as much, is because here's the magic show a little bit of where you need to pull out of your hat the appropriate form of a particular solution based on what is the form of g of t, right? And you pull out and you use this form of that particular solution, but you leave some of the coefficients of that underdetermined to give you some degrees of freedom to solve later on down the road. And in fact, down the road is actually step number 4, because what you're going to then do is go ahead and plug your particular solution into your differential equation and then use those undetermined coefficients to make the left-hand side equal to the right-hand side, okay? Once you have both the homogeneous and the particular solution, you can add them together to get the total solution here. And then lastly, you can at that point go ahead and apply the initial conditions to find C1 and C2, right? So that's the traditional approach, so it works out okay. And now the other way you could have done this is you could have gone the Laplace method, right? So the Laplace technique would have said, okay, just take this equation right here, it's a non-homogeneous differential equation, I really don't care, just apply the Laplace transform to both sides, just apply the Laplace integral to all the terms on the left and all the terms on the right, and just there you go. Once you have that completed, you can basically solve for the signal of interest, but in the Laplace domain, right? Big X of S. Just do that using algebra, right? Once you've done that, you can go ahead and use the techniques we outlined to do the partial fraction expansion to get that X of S into a desirable format, which you can then just directly inverse Laplace transform, or cheat and run over to Mathematica and just say inverse Laplace transform, right? That's the other way you could do it. So again, multiple ways to go about it, multiple ways to skin this cat. Pick your poison, whatever is interesting for you. So with that being said, I think this is a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos, and I hope to catch you at a future one. Please leave me a comment below if there's a topic you'd like me to discuss in the future, or if something wasn't clear, you'd like to follow up or start a discussion there. That is a great place to do it. And again, the new videos come out every Monday, so I hope I'll catch you at one of those. So until we talk again, I think I'll sign off for now. Bye.